So it was mentioned in the last section that R squared really shines when we want to make comparisons between models. And so we're going to see how that works put into practice with this example. So we have a list of R values here. And this might not be the list that's shown in your notes. So if it isn't, make sure you change to these numbers. That's a typo that I need to fix for future semesters. So we want to circle and label the strongest relationship, and we want to box and label the value for the weakest relationship. Okay, so if we look at the R values here and just compare across, the strongest relationship, remember R values, the strongest relationships are close to 1 and -1. So the strongest relationship is actually the -0.88, the first one, because that is strong, unlike the other ones, which is moderate and weak, and it's the closest to 1 or -1. So it's the strongest one out there. Now the weakest relationship, weakness is close to 0 for R. So you want to look for where the 0 is, or the closest value to 0. And the closest value to 0 is right here. So we're going to box that, right? Because 0.34 is the smallest number out there. The positive and negative doesn't really matter. Right? All that matters is the size of the number. In math and science, we call it the magnitude, right? The magnitude of the number. Okay, so now let's look at B. Well, B cuts out all the negative positive stuff. So this is where R squared is actually a little easier to work with even than R, because whichever number's the biggest, that's the strongest, and whichever one number's the smallest, that's the weakest. So the strongest is right here, because 81 is the biggest. Right? We don't have to think about the positive and negative and all of that. Right? Biggest number is closest to 1. Weakest number is actually the closest to 0, which is right here. It's much more straightforward because for R squared, it's only between 0 and 1. It doesn't have that whole other side to things. So it's much more straightforward. There's only a few sections that it could be. Okay, now what if it's a mix and match situation? What if some of them are R's and some of them are R squareds? Well, in that case, what you should do is turn them all into R squareds. So you take 0.68 and you square it. So let me grab Desmos real quick. So I take 0.68 and I want to square it. Now if you pull up the palette, it's the A squared button right there, or it's a shift 6 above your 6 button. There's a little caret button, and that would also raise it, and then you have to hit the 2. So 0.68 squared is 0.4624, and while I'm at it, 0.71 squared is 0.5041, right? So what you want to do is you want to write these values in right below where they are on the paper. Now, if you're thinking about the negative, why is it's negative 0.71? Well, if you put a negative inside and you close your parentheses and square it, it still turns positive, right? Because a negative times a negative is a positive. Negative 0.35 squared would be 0.1125. So it's easiest to turn all of them into R squareds, right? Remember, if you have R and you want R squared, you just square it. Now we can really make comparisons. Now we can see which of these numbers is the biggest and the smallest. Because whichever one's the biggest, that's going to be our strongest relationship, right? Because whichever one's closest to 1. And the closest number to 1 is actually right here. 58 is the biggest number out there, 0.58. So this is the strongest relationship. The weakest relationship is actually over here, right? Because the weakest, oops, this is a box. Box. The weakest is the closest to 0. So you can see that for making direct comparisons from one to the other, R squared is a lot easier to work with than R. And it's very straightforward. Right? Whichever is the biggest number, that's the strongest. Whichever is the smallest number, that's the weakest. So we want to be able to find R squared from a data set, and we're going to do that with StatCrunch, right? We never find anything in this chapter by hand. So we've seen this data set before, so let's go grab it again. So I'm going to go to my chapter 4 data set, and this is the free reduced lunch one. So I'm going to click on that link and click right there. All right, so it has the free reduced lunch on the first column and the passing math on the second column. We go to stat, regression, simple linear. The first column is always our x and the second column always our y. That's just the way I set up the course. And then I click compute because none of the rest of that matters. And remember, this is giving us a whole bunch of information that we don't need. All we need is in this top section right here. R squared, SQ stands for squared, right? So that's your coefficient of determination. So R squared is 0.473 if you're doing 3 decimal places. And I wrote RSQ because that's what R squared is. All right, now we want to interpret this value. Well, there's a script for interpreting it on the previous page. What we do is we take that R squared value and we multiply it by 100. In other words, we're moving the decimal 2 spots to the right to make it into a percent. Okay, so we will say, oh, first before I go any further, let me just make a note. Right, this is R squared, and this was found with stat, regression, simple linear. Okay, so some percent of the total variation in, and then we write what the y variable is explained by the least squares regression model. This is an extremely rigid script. We do not mess with this script. We are just going to write it. All we have to do is figure out what we're going to put in for our 2 blanks, and we're set. So over here, we're going to write what the y variable was. So the y variable is right here. It was the percent of students passing the math test. So that way we say percent passing the math exam, right there. And then we have to turn our value, which is a decimal currently, into a percent. So we multiply it by 100. In other words, you move the decimal 2 spots over, right? Take it from this place to the hundredths place. And so it becomes 47.3% of the total variation, and the percent passing the math test is explained by the least squares regression model. Or you could say least squares regression line. Stick with that script and do not deviate. So let's do another example. This is the same fertility rate and life expectancy we've seen several times. Remember, this is our x variable, this is our y variable. Actually, this is x right here. All right, so what's the coefficient of determination? Well, the coefficient of determination is r squared, and r squared was given. It's right here. It's 0.5189. Okay, so compute the correlation coefficient. That's a little bit tricky. So the correlation coefficient is r. So you'll remember, we know that r is equal to plus or minus the square root of r squared. And you have to choose based on slope. Okay, so we keep this in mind. Right? This is our kind of our formula right here. All right, so let's do this. So r is equal to the square root of 0.5189. And technically, it's going to be the negative on this one. Now, why do I choose negative? So I'm choosing negative because the slope is negative. So you can see right here, the slope is negative. You can also see right here, the slope is negative. This is a decreasing line. So since the slope is negative, that means my r is negative. So that's why I'm choosing a negative value. All right, so all I have to do now is go find that with Desmos. That's not a StatCrunch thing, that's a Desmos thing. So let me go grab Desmos. And I want to take the square root. Now, square roots you can get to a couple ways. They are in the palette. It's the check mark symbol that's next to the pi. So you could type it like that. Or if you type SQ for square, SQRT for root. SQRT. If you type those 4 letters in a row, it knows what you want and it brings up the square root. So either way you like it, you're going to get the R value is about 0.720. And of course it's negative because our slope is negative. So that means R is negative 0.720. And let's make a little note. This symbol is SQRT in Desmos, if you want to type it rather than using the palette to bring it up. All right, now we want to interpret R squared, right? So that's not R, that's R squared. We're going back to R squared. So we want to take our value and we want to fill it into the script. So some percent of the total variation in the y variable is explained by the least squares regression model. Or regression line, either way. Okay, so all we have to do is fill in what the y variable was. Well, the y variable was life expectancy, so we're going to put that in. Right? Remember, these are words, not numbers. So that's life expectancy. And then we want to take our R squared value, which was 0.51819, and we want to move the decimal 2 spots over to the hundredths place. And we say 51.89% of the total variation in life expectancy is explained by the least squares regression line. Now, a politician from another country sees our data and those results for life expectancy and fertility rates. She determines that to get a longer life expectancy in her country, she should just restrict the number of children to 1 child per woman. What is wrong with this reasoning? Okay, this is a problem with correlation and causation, right? Yes, more children leads to lower life expectancy, but that's not because of the children necessarily, right? What's happening is that there's other things going on. So remember our classic correlation is not causation. Now, why is that? That's because there are lurking variables such as, and then we'll figure out a few in a second. Sorry, such as is not one word, so let me make that separate. So such as, and then we'll figure something out that affect fertility and life expectancy. And remember, this was in 1962 as well. Fertility right? This wasn't modern times. This was many, many years ago. Okay, so what are some possible things that are going on? These are countries, right? So why would a country have higher fertility and lower life expectancy? Why would a country have lower fertility and higher life expectancy? What's going on? And one of the obvious things would be income, right? So you're seeing GDP, right? Gross domestic product, how much the country makes, right? The income of the country, in other words, money. Another thing you're seeing is infrastructure, medical infrastructure, healthcare, in power, energy, etc. There's all sorts of things. Infrastructure is one of my favorite words, right? Because it's affecting everything in that country, including like power lines and how much water you have. Do you have clean drinking water in the country, etc. So there's a lot going on in these countries, and they would affect both the fertility and the life expectancy. Right? Remember that when you're looking for a variable, a lurking variable, you're looking for something that affects both x and y. So let's just make a note.